Hello everyone, welcome to our class. In this class, we will study Chapter 9, Convection. Firstly, we will discuss convection boundary theory. As we know, convection will occur between a moving fluid and a solid surface when their temperature is not the same. Convection is divided to forced convection and natural convection. One question: Newton's law of cooling. The heat transfer from a solid surface of area A at a temperature Ts to a fluid of temperature T infinite is given by Q equals H times A times temperature difference Ts minus T infinite. This equation is very famous. We can call it Newton's law of cooling, where H is the convection coefficient. A is the area convection between fluid and solid surface, the area. The temperature difference Ts minus T infinite. Q is always implies. If Ts larger than T infinite, the temperature difference is Ts minus T infinite. If Ts smaller than T infinite, the temperature difference is T infinite minus Ts. Always Q is plus, positive. We can call it the heat transfer flow rate. The unit is watt per square meters times degree and the turbulent flow. Okay, for different position on the surface, under the solid surface, certainly the heat transfer flow rate is different. The coefficient H also is different. We can think it is variable because the flow situation and temperature distribution is not same in different position points. For whole surface, we can do some integration. For example, Q integration for whole the area A, integration Q dA is the whole the heat transfer flow rate, H times temperature difference dA integration for whole the surface. If the temperature is uniform on the surface, certainly Q equals temperature difference Ts minus T infinite, also times integration for whole the surface H dA. Here is the whole the surface, the heat transfer flow rate. Generally, H is very difficult to be determined because the convection processes are related to many factors. As we know, many factors influence on the H, show flow rate. For example, flow rate, properties of the fluid, the shape and the position of the solid. Many factors have influence on the coefficient H. Therefore, H is very difficult to obtain. So in Newton's law of cooling, the equation, all the complex and the difficulty of the convection in Newton's equation, I concentrated to the convection coefficient. The key work is to calculate the coefficient, convection coefficient. The second one, convection boundary layers. As we know, the velocity of fluid has so much influence on the convection. Firstly, velocity boundary layer. As we know, velocity boundary layer is formed as follows. Here is a plate. When fluid over the plate, overflow the plate. When it close the plate, because some fluid, the velocity becomes smaller. So close to the plate, there is a layer. The velocity change very big. We can call it velocity boundary layer. Velocity boundary layer will be produced when the free stream from the plate. Here is the free stream very close to the plate because the friction is not ignored. So the velocity becomes small, become bigger. So formed a boundary layer. Boundary layer, there is some reasons, because firstly is friction or viscosity of the fluid. The fluid close to the solid is stopped because the friction or viscosity in the fluid. Also, another reason is due to the viscosity, the flow rate of the fluid is decreased, especially for the fluid near to the surface of the solid, because the solid, between the solid and the fluid, there is some friction, viscosity, so the flow rate is influenced by the friction, by the viscosity. At the position of y equals 0, flow in the tube become 0. From this point, you will increase with the distance y to the surface. Over a layer, you will reach the main flow velocity u infinite, because from here the flow rate becomes smaller, become bigger. Then the distance is very big. When the y is bigger, so the u become u infinite. This layer is called velocity boundary layer. Sometimes we can call it boundary film. The thickness is that. That is the thickness of the layer. In the layer, the flow in U reaches 99% of U infinite is just the boundary. So it is noticeable that will change with the position x. So the layer become more thickness as the x increase. About velocity boundary layer, we can give more discussion. According to Newton's viscosity law, the viscosity force tau is proportional to velocity gradient in vertical direction. That tau equals mu plus u plus y is very famous, the equation. We can call it Newton's viscosity law. Here, mu is called dynamical viscosity. The unit is kilogram per meter per second. In the layer, because partial U, partial Y is very big, so tau is not able to be ignored. Also, the flow situation within velocity boundary layer, there is very big change. The situation is there is very big change. At the first part, from x equals 0 to xc is most case is the laminar flow. From x equals xc with the x increase, maybe the flow is not stable, it's not steady, become more and more turbulent. So in this from xc to some distance, we can call it transition region. After the transition region, the flow become very complex, very turbulent. So in this region, we can call it turbulent flow. However, close to the plate, very close to the plate, there is a very thin layer. We can call it buffer level viscosity layer. Very thin layer. In this layer, because the flow rate is very small, we can think it is always laminar flow. We can do more discussion. With that increase, when x larger than xc, this region we can call it unstable region. Also, turbulent flow become turbulent flow. The third region, there is a very thin layer we discussed, is very close to the plate, very close to the surface. In this layer, the flow always keeps laminar flow because very close to the plate, influenced by viscosity, by friction, the flow rate is very small. This layer called as laminar sublayer with thickness of delta C. Delta C is very small, it's not so big. Okay, we know there is some viscosity boundary layer. If the plate the temperature and the working fluid, the fluid, the temperature is not same, certainly will be produced some thermal boundary layer. For example, if the plate temperature is Ts, the fluid the temperature is T infinite. Ts not same as T infinite. A thermal boundary layer will be occurred. If Ts larger than T infinite, the thermal boundary layer like this. Close to the plate, in this region, the temperature is larger. The distance increase, the temperature becomes small. So the thermal boundary layer lost this picture. If the temperature Ts is smaller than T infinite, the boundary layer like this, close to the plate, the temperature is small, bigger, larger. So it's different. When the surplus temperature Ts minus T equals 99% of Ts minus T infinite, in this region we can call it just is the thickness of thermal boundary layer. We can use delta T to express it. Similarly, if the fluid is cooled by the solid surface. It also has the similar thermal boundary layers. It's similar. It's cooled, is heated, different, because the surplus temperature is just opposite. But the thermal boundary layer is similar. Whether heating or cooling, the flow field is always divided into two regions. One is thermal boundary region with temperature severe change. The second is mainstream isothermal region, in which the temperature distribution is uniform, divided into two regions. Delta T and delta is different concept, is not always same. Delta T is thermal boundary layers, the thickness. Delta is velocity boundary layer thickness. It is two concepts. It's not always same. Just to say delta T and delta is not same. It's not same. Most of the case is different. Near to the surface of the solid, because the velocity of the fluid is zero. The heat transfer only has the conduction. That's to say, the local heat flux can be calculated by Fourier's law as follows. Just to say, because very close to the plate, the layer, the flow rate is very small. So the heat transfer is only has the conduction. So in this case, we can use conduction equation to calculate the heat flow rate. Qx equals minus K is conductivity. Partial T partial Y at Y is 0. So for example, here is the X point, X region. In this part, the heat flow rate, heat flux, Qx equals minus K partial T partial Y at Y is 0 from the conduction. On the other hand, from Newton's law of cooling, we can calculate the heat transfer by convection. So Qx equals Hx times Ts minus T infinite temperature difference equals Hx times delta T from the convection. Certainly, this equation, the Qx, is the same thing. By these two equations, we obtained Hx equals minus K over delta T times partial T partial Y at Y is 0. So from conduction and convection, we can calculate Qx. So we obtained very good the equation. We can use this equation to calculate the coefficient at x. Okay. Therefore, to calculate the Hx is transferred to calculate partial T partial Y at Y is 0. Generally, also to relate it to the velocity distribution in the velocity boundary layer. So in this layer, partial T partial Y is difficult to calculate. Because the temperature gradient in the boundary layer is changed very big. So sometimes it's very difficult to calculate. But from principle, the H always relationship partial T and partial T over partial Y at y is 0. From this equation, also from the thermal boundary layer, we can think the temperature gradient in the boundary layer is change. So also will decrease with x. So Hx in same region will decrease with the x, because the thickness of thermal boundary layer is change big, become big with the x. So Hx is decrease with the x. So decrease when x become larger in the same region. However, when laminar flow become turbulent flow, the Hx certainly there is very big change. The heat transfer coefficient will have very big change in different flow situation. For example, laminar flow is the Hx is small. Turbulent flow, the Hx become very big change. Okay, the heat transfer coefficient will decrease with increased x in same flow pattern. However, Hx in turbulent region is much bigger than that in laminar flow. So most case, we can obtain this diagram. The vertical axis is h, horizontal axis is x. The h in laminar flow decrease. However, in turbulent flow suddenly increase, rapidly increase. From here become decrease. Change decrease very small. It's not so big change. However, the thickness of thermal boundary layer originally is very small. Is this line, this curve increase, suddenly increase. So it's different pattern. Okay, thank you.